Hello, my name is Paul Geyer, and I'll be talking with you today about impressed current cathodic protection systems. This is what I'll be talking about, kind of the chapters in the book, you might say. First, some introductory comments. Second, determination of circuit resistance. Third, determination of power supply requirements. Fourth, selection of power supply type. Fifth, rectifier selection. Sixth, anodes for impressed current systems. And seventh, other system components. This, for background information, is just a little bit about me and what I've been doing for the last few decades. By way of introduction, there are two principal methods of providing cathodic protection: sacrificial anode and impressed current. The primary advantage of impressed current cathodic protection systems over sacrificial anode cathodic protection systems is that the driving potential of the impressed current systems is not limited by the corrosion potential of an active metal. The ability to select appropriate driving potentials and to adjust the driving potential after system installation gives the designer and operator of impressed current cathodic protection systems additional flexibility to compensate for changing environmental conditions. The primary advantage of this variable driving potential in the design of impressed current cathodic protection systems is the ability to select the location of anode beds for an optimum distribution of protective current with a minimum interference. The variable driving potential available in impressed current systems also allows the protection of structures in high resistivity environments where the output of sacrificial anodes is severely limited. The primary operational benefit of variable driving potential is the ability to adjust the system for changes in soil resistivity, anode condition, structure surface, that is the coating condition, and additions to the structure. In the design of impressed current cathodic protection systems, the first step is the determination of the total current required for the system. This fixes the output current required for the system power supply. The next step is the determination of the required output or driving potential that will be required. As the output current is fixed, the required driving potential will be determined by the local circuit resistance and the back potential offered by the circuit anode potential. The equivalent circuit is shown in Figure 1. In most impressed current systems, the major factor in the determination of the total circuit resistance is the anode to electrolyte resistance. With regard to the anode to electrolyte resistance, also known as ground bed resistance, this is often the highest resistance in the impressed current cathodic protection system circuit. As shown in Figure 1, the anode to electrolyte resistance, if high, is the most important factor in the determination of the driving potential required to provide the current required for effective cathodic protection in impressed current cathodic protection systems. Anode to electrolyte resistance can be varied within wide limits by the use of different sized anodes and the use of multiple anodes. The lowest anode to electrolyte resistance commensurate with total system cost is desirable, since it will reduce the power costs by lowering the output potential of the power supply. This lower power supply output potential also results in higher reliability for other system components, particularly the insulation on cables, splices, and connections. In general, anode bed resistances below 2 ohms are desirable. Figure 1 indicates the equivalent cathodic protection circuit. Anode to electrolyte resistance can be computed from data on anode type, size, shape, and configuration of multiple anode arrays plus the soil resistivity. First, the type, size, and shape of the anode to be used is chosen. Then the resistance of a single anode to be used is calculated. Then the effect of the use of multiple anodes is determined. However, as the actual environmental resistivity may not be uniform or may undergo seasonal variations, the calculation of anode to electrolyte resistivity should only be considered to be an approximation of the actual resistance to be encountered. This can result in the actual driving potential required being somewhat different than the potential calculated using the approximate anode bed resistance. Thus, after installation, the driving potential must be adjusted to give the required current output. As the other potentials and resistances in the cathodic protection circuit vary, the system will also require periodic adjustments. The formula developed by H.B. Dwight for a single cylindrical anode can be used to determine the anode to electrolyte resistance. The formula for a vertically oriented anode is as represented here, with the components identified. The formula for a horizontally oriented anode is as also indicated here. For many common situations, the Dwight formula have been simplified by combining terms and eliminating terms that have insignificant values in most cases. Some of these simplified formula have been given. In addition to these simplified formula, the following simplified formula is often used. For resistance of a single vertical anode, the formula provides for the following indicated on this slide. Common practice to reduce anode bed resistance is to connect several anodes in parallel in a group. The resistance of a group of anodes is less than the resistance for a single anode, but is greater than that calculated from the usual parallel resistance formula due to interactions between the fields surrounding each anode. If the anodes are arranged in a parallel row, the resistance of a group of anodes can be approximated by the following formula. The formula is indicated on this slide. If multiple rows of anodes are used where the spacing between rows is more than 4 times the spacing between the anodes in each row, the usual parallel resistance formula indicated here may be used. For water tanks where circular arrays of anodes are commonly used and where the structure surrounds the anodes and electrolyte, special formulas have been developed to calculate the anode to electrolyte resistance. For a single cylindrical anode, the formula developed by E.R. Shepard may be used. The formula is as follows, and indicated on this slide. The anodes are usually arranged in a circular array in the tank bowl. The optimum diameter of this array can be determined by the following formula indicated here. If 4 or more anodes are used in a circular array, the following modified Shepard formula should be used to calculate the resistance of the array, as indicated on this slide. Calculations, as previously discussed, can give good approximations of anode to electrolyte resistance under actual conditions. While these calculations can be effectively used for system design if the environment is well known, the actual anode to electrolyte resistance that is encountered is sometimes sufficiently different from the calculated value to require adjustment or modification of the system. The actual anode to electrolyte resistance can also be determined by actual field measurements. With regard to the anode first method, in this method of determining anode to electrolyte resistance, the anodes are installed as designed and the actual resistance between the anode or anode bed and the structure to be protected is measured. This measurement includes both the anode to electrolyte resistance and the structure to electrolyte resistance, and can be used to determine the required driving potential so that the power proper power supply can be ordered. This is the most accurate method of sizing the needed rectifier and should be used where practical. With the power supply first method, the power supply is ordered based upon the calculated circuit resistance and is installed and connected to the structure. The anodes are installed as planned, but one at a time. The total circuit resistance is calculated based upon the actual power supply output in amperes and volts. If additional anodes are required in order to achieve the desired anode to electrolyte resistance, they can be installed at this time at a relatively low cost, since the equipment required for installation is on site and excavations for the anode lead cables are open. Backfill is very important and is usually used to surround impressed current anodes in order to reduce anode to electrolyte resistivity, to increase porosity around the anodes to ensure that any gases formed during operation will be properly vented, and to reduce polarization effects and reduce localized dissolution of the anode. Under favorable circumstances, the anode to electrolyte resistivity can be reduced to 1/2 through the use of backfill. In extremely low resistance environments such as seawater, graphite, and high silicon cast iron anodes can be used without backfill. Otherwise, impressed current anodes should always be used with backfill. In high resistivity environments where the use of backfill is impractical, graphite anodes should not be used. High silicon chromium bearing cast iron anodes can be used with or without backfill in most instances. The cost of using backfill should be evaluated on an economic basis, with the reduction in the power requirements of the anodes required being the cost reduction factors. If the resistivity of the backfill is less than 1/10 the soil resistivity, then the voltage drop through the backfill becomes negligible. Thus, the effective diameter of the anode is the diameter of the backfill rather than the diameter of the anode itself. As can be evaluated through calculation of anode to electrolyte resistance, this can result in a significant reduction in anode to electrolyte resistance, which can be useful in reducing the number of anodes required, the required driving potential, or both. Backfill for impressed current anodes is carbonaceous material from several sources. It can be either coke breeze, crushed coke, flake graphite, or round particle petroleum coke. Experience has shown that round particle calcined petroleum coke has many advantages over coke breeze made from coal. Specification Loresco DW2 or equal should be used for surface anode beds, and Loresco DW3 or equal for deep anode beds. Because the material can be pumped and has good porosity and particle-to-particle contact, round particle petroleum coke backfill is the most desirable material, and its higher cost will be justified for most installations, particularly for deep anodes. In areas where the soil is extremely wet or loose, such as in a swampy area, it may not be possible to properly install or tamp the backfill material. Packaged anodes with the backfill contained in metal cylinders or cans surrounding the anodes may be useful in these circumstances, but it increases the cost. Anodes pre-packaged with backfill, usually contained in metal cans which are rapidly corroded away during operation, are easier to install than separate installation of anode and backfill. The pre-packaged anodes are higher in cost and have the following additional disadvantages. First, high unit weight reduces ease of handling. Second, possibility of voids developing in backfill during transportation and handling. And third, the critical anode cable and connection between the anode and cable are hidden and difficult to inspect. The choice of packaged versus unpackaged impressed current anodes must be made based upon economics and local site conditions. Packaged anodes are usually used only where unstable soil conditions exist, where the hole excavated for installation caves in, and where prepackaged anodes are stocked for augmenting systems. With regard to the structure to electrolyte resistance, the structure to electrolyte resistance is commonly disregarded in the design of impressed current cathodic protection systems, since it is usually very small with respect to the anode to electrolyte resistance. When the total circuit resistance is measured, the structure to electrolyte resistance is included in the value obtained. The connecting cable resistance is determined by the size and length of cable used. In addition to the fact that connections and splices are sources of resistance in impressed current cathodic protection systems, they are a site of failure. These connections should be kept to an absolute minimum, and they should be very carefully assembled, insulated, inspected, and installed. The cable from the positive lead to the power source to the anodes carries a high positive charge and will deteriorate rapidly at any point where the insulation is breached and the conductor contacts the electrolyte. The number and location of each connection should be installed per the system design and not at the discretion of the installer. The power supply requirements, namely the current and voltage, are determined by Ohm's law from the required current for protection of the structure and the calculated or measured total circuit resistance. The actual power supply requirement should allow for future loads and rectifier aging. Generally, a factor of 1.5 over calculated output is used. The connecting cable resistance is determined by the size The power supply requirements must be determined. The power supply requirements, namely current and voltage, are determined by Ohm's law from the required current for protection of the structure and the calculated or measured total circuit resistance. The actual power supply requirement should allow for future loads and rectifier aging. Generally, a factor of 1.5 over calculated output is used. Any source of direct current of appropriate voltage and current can be used as a source of power for impressed current cathodic protection systems. The selection of the power supply depends upon local conditions at the site and should be evaluated based upon life cycle cost, including maintenance and availability of AC power or fuel. Rectifiers are by far the most commonly used power supply type for impressed current cathodic protection systems. They are available in a wide variety of types and capacities, specifically designed and constructed for use in impressed current cathodic protection system. The most commonly used type of rectifier has an adjustable step-down transformer, rectifying units called stacks, meters, circuit breakers, lightning arrestors, current measuring shunts, and transformer adjusting points or taps, all in one case. Thermoelectric generators are power supplies that convert heat directly into direct current electricity. This is accomplished through a series of thermocouples which are heated at one end by burning a fuel and cooled at the other, usually by cooling fins. Thermoelectric generators are highly reliable since they have few, if any, moving parts. They are available in sizes from 5 to 500 watts. They are very expensive and should only be considered for remote locations where electrical power is not available and fuel is available. They are used as a power supply for impressed current cathodic protection on remote pipelines where the product in the pipeline can be used as a fuel. With regard to solar power supplies, a photovoltaic solar cell converts sunlight directly into direct current electricity. The cost per watt is high but is decreasing as solar cell technology is improved. Solar panels are used for cathodic protection power supplies at remote sites where neither electrical power or fuel is available. In order to supply current continuously, solar cells are used in a system that supplies power to the system and recharges batteries when sunlight is received. When sunlight is not received, the batteries supply the required current. With regard to batteries, when current requirements are low, storage batteries can be used to supply power for impressed current cathodic protection systems at remote sites. They must be periodically recharged and maintained. Generators, engine or wind-driven generators, can be used to supply direct current power for impressed current cathodic protection systems at sites where AC power is not available. Rectifier selection is an integral part of the design process. The rectifier selected for a specific impressed current cathodic protection application must be matched to both the electrical requirements and the environmental conditions at the site. Rectifiers are available in many electrical types and specifically designed for use in impressed current cathodic protection systems in many environments. Figure 2 is a circuit diagram for a typical single-phase full-wave bridge-type rectifier showing the components found in most standard rectifiers of this type. The diagram also shows an external switch and circuit protection device, which is mandatory for many rectifier installations. The transformer reduces the incoming alternating current voltage to the alternating current voltage required for the operation of the rectifying component. In most impressed current cathodic protection rectifiers, the voltage output from the secondary windings can be varied by changing the effective number of secondary windings through a system of connecting bars or taps. Two sets of taps are normally present, one for coarse adjustments and one for fine adjustments. By manipulation of these taps, the voltage should be adjustable to vary the rectifier voltage from 0 through at least 20 equal steps to its maximum capacity. The alternating current from the secondary windings of the transformer element is converted to direct current by the rectifying elements or stacks. The stack is an assembly of plates or diodes and may be in several configurations. The most common rectifying elements are selenium plate stacks and silicon diodes. Each has advantages and disadvantages. The most common configurations of rectifying elements are the single-phase bridge, single-phase center tap, three-phase bridge, and three-phase Y. The rectifying elements allow current to flow in one direction only and produce a pulsating direct current. The rectifying elements do allow a small amount of alternating current to pass. This ripple is undesirable and should be held to low levels. Rectifiers are not 100% efficient in converting alternating current to direct current. This is due to the presence of alternating current and to inherent losses in the rectifying elements which result in heating of the stacks. Silicon elements are more efficient than selenium elements at high output voltages, but are more susceptible to failure due to voltage overloads or surges. The efficiency of a rectifying element is calculated by the following equation, as indicated on this slide. Typical efficiencies of single-phase rectifying elements are in the order of 60 to 75%, but can be increased by filtering the output or by using a three-phase circuit. Overload protection in the form of either circuit breakers, fuses, or both should be used on all impressed current rectifiers. In addition to protecting the circuits from overload, circuit breakers provide a convenient power switch for the unit. Circuit breakers are most commonly used on the alternating current input to the rectifiers, and fuses are most commonly used on the direct current outputs. In addition to circuit breakers and fuses, the rectifier should be furnished with lightning arrestors on both the AC input and DC output in order to prevent damage from lightning strikes or other short-duration power surges. The respective firing voltages of the lightning arrestors should be higher than the AC input and DC output voltage. Due to their susceptibility to damage from voltage surges, silicon diodes shall also be protected by selenium surge cells or Resistors and by current-limiting fuses against overcurrent surges. A high-speed rectifier fuse should be installed in one leg of the AC secondary and one in the DC negative output leg. Figure 2 indicates a single-phase, full-wave bridge rectifier. In order to conveniently measure the output current and potential, the rectifier should be furnished with meters for reading these values. The meter should not be continuously operating but should be switched into the circuit as required. This not only protects the meter from electrical damage from surges, but when the meter is read, it moves from 0 to the indicated reading. Frozen meter movements are easily detected in this manner. Often 1 meter and a 2-position switch are used to measure both potential and current. Current is usually measured using an external current shunt. Output voltage and current can also be conveniently measured by the use of portable meters used across the rectifier output and the current shunt. With regard to the standard rectifier types, the single-phase bridge, the circuit for this type of rectifier is shown in Figure 2. This type of rectifier is the most commonly used type of rectifier up to an output power of about 1,000 watts. Above 1,000 watts, the extra cost of 3-phase types is often justified by the increased electrical efficiency of the 3-phase units. The rectifying unit consists of 4 elements. If any one of the rectifying elements fails or changes resistance, the other elements usually also fail. Current passes through pairs of the rectifying elements through the external load, the structure and anode circuit. The active pair of elements alternates as the polarity of the alternating current reverses, while the other pair blocks the flow of current. The result is full wave rectified current as shown in Figure 3. With regard to the single-phase center tap type, the circuit of a single-phase center tap rectifier is shown in Figure 4. This type of rectifier has only 2 rectifying elements but produces full-wave rectified output. However, since only 1/2 of the transformer output is applied to the load, the transformer required is considerably heavier and more costly than in single-phase bridge-type units. This type of unit is also less sensitive to adjustment than the single-phase bridge type. However, it is electrically more efficient. With regard to the 3-phase bridge, the circuit for a 3-phase bridge rectifier is shown in Figure 5. The circuit operates like 3 combined single-phase bridge circuits that share a pair of diodes with one of the other 3 bridges. There are 3 secondary windings in the transformer that produce out-of-phase alternating current supplied to each pair of rectifying elements. This out-of-phase relationship produces a direct current output with less alternating current ripple than the single-phase type, only 4.5%. Due to the reduction in alternating current ripple, 3-phase bridge rectifiers are more electrically efficient than the single-phase types, and the extra initial cost of the unit is often justified by savings in supplied power, particularly for units over 1,000 watts capacity. Figure 3 indicates the full wave rectified current. Figure 4 is a schematic for the single-phase center type circuit. Figure 5 indicates the 3-phase bridge circuit schematic. The circuit for a 3-phase Y rectifier is shown in Figure 6. This type of rectifier supplies half-wave rectified current as shown in Figure 7. The power to the rectifier unit is supplied by 3 separate windings on a transformer, but only 3 rectifying elements, each in series with the output, are provided. This type of rectifier unit is practical only for systems requiring low output voltages. Several special rectifiers specifically designed for use in cathodic protection systems have been developed for special applications. Some special rectifiers provide automatic control of current to maintain a constant structure to electrolyte potential. Others provide a constant current over varying external circuit resistances or other features desirable in specific circumstances. A constant current rectifier is depicted by a block diagram in Figure 8. A direct current input signal to the power amplifier is supplied from an adjustable resistor in the output signal. The power amplifier uses this feedback signal to adjust the voltage supplied to the stack so that a constant input signal and therefore a constant output current is supplied. The power amplifier may either be of an electronic silicon-controlled rectifier or saturable reactor type. An automatic potential control type is shown by a block diagram in Figure 9. This type of unit uses the potential between the structure and a reference electrode to control the output current of the unit. As in the constant current type of rectifier, the power amplifier can be of the electronic or saturable reactor type. These rectifiers are commonly used where the current requirement or circuit resistance varies greatly with time, such as in the case of a structure in an area with high periodic tidal currents or a water storage tank where the water level changes considerably. Figure 6 indicates the three-phase Y circuit. Figure 7 indicates the half-wave rectified circuit. Figure 8 is a schematic for the constant current rectifier. Figure 9 is a schematic for the constant potential rectifier. Multi-circuit constant current type is depicted by a circuit diagram in Figure 10. This type of rectifier is designed to provide a small constant current in the order of 100 milliamperes to a single anode. As the resistance of the internal resistor is high when compared with the external circuit resistance, the output current is controlled by the value of this resistor. The output potential will vary up to the line voltage to supply the specified output current. In this type of circuit, the structure is connected directly to the neutral lead of the alternating current power supply. Due to problems associated with stray currents and the possible presence of high voltages external to the rectifier unit, the use of this type of rectifier is not recommended. Several standardized rectifiers have been developed for commercial applications such as natural gas and electrical distribution system protection. The use of a standardized unit allows for economy of production and reduction in overall cost of the unit, as well as the installation and maintenance of the unit. Where a large number of similar capacity units are to be used, the selection of a standardized type of rectifier shall be considered. Rectifiers can either be selected from stock units or can be custom manufactured to meet specific electrical and site-related requirements. Many features are available either as add-ons to stock units or in custom units. Figure 10 indicates the multi-circuit constant current rectifier arrangement. Available features on these units include constant voltage or current output, multiple circuits in the same enclosure, air-cooled or oil-immersed, commercial input voltage, three-phase or single-phase, center tap or bridge, wide range of output currents and voltages, efficiency filters to reduce AC ripple, interference noise filters, explosion-proof enclosures, small arms proof enclosures, lightning protection on both AC input and DC output, surge protection on both AC input and DC output, silicon diodes or selenium stacks, painted or galvanized cases, various mounting legs or brackets, units designed for direct burial, external on-off indicators, a variety of price, quality, and warranties, and maintenance-free anodized aluminum enclosures. Factors that should be considered in selecting appropriate features for a specific application are discussed below. First, air-cooled versus oil-immersed. Rectifiers can be supplied as either entirely air-cooled, entirely oil-immersed, or with the stacks only oil-immersed. Air-cooled units are lowest in cost and easiest to install and repair. However, oil-cooled units should be specified where corrosive or dirty atmospheric conditions are encountered or where explosive gases may be present. The controls should not be immersed in the oil. Air-cooled units require more frequent maintenance to clean the air screens and other components and are also susceptible to damage by insects and other pests. Older oil-cooled units were supplied with oils containing polychlorinated biphenyls, PCBs, which have been determined to be carcinogenic and are no longer supplied with new units. Units containing PCBs should be treated according to current policy regarding PCBs. With regard to selecting the AC voltage, select alternating current voltages of almost any commercial power supply voltage. Units with either 115, 230, or 440 single-phase or 208, 230, 440 three-phase inputs are the most common. Some units are supplied with dual input voltage selected by wiring arrangements during installation. Choices between single-phase and three-phase units should be based upon a balance between first cost and efficiency. The table below can be used to select the combinations of rectifier capacity and input voltages which are commonly most economical if a selection of supply voltages is available. With regard to DC voltage and current output, direct current voltage outputs from 8 to 120 volts and current outputs from 4 amps to 100 amps are common. Almost any current can be provided, but it is generally best to select a smaller standard size rectifier such as 20 amps and use multiple units if very large amounts of current are required. Many small units cause far less interference and provide more uniform current distribution along the protected structure than few large units. With regard to filters, electrical filters are used to both increase the efficiency of the rectified by reducing alternating current ripple and to reduce interference with communications equipment. Efficiency filters can increase the efficiency of single-phase bridge-type rectifiers by 10 to 14%, and their use should be based upon a first cost versus operating cost basis. Efficiency filters are not commonly used with three-phase rectifiers as the alternating current ripple in these units is inherently low. Noise interference filters should be used when a large unit is to be installed in the vicinity of communications lines or can be retrofitted when noise problems are encountered and are significantly affected by turning the unit on and off. Rectifiers and other system components such as switch and circuit breakers are available in explosion-proof enclosures conforming to electrical safety standards for Class 1 Group D hazardous conditions that may be encountered in fuel or natural gas storage or distribution systems. Such enclosures should be specified whenever explosive hazards may exist. Lightning arrestors should always be used on both the AC input and DC output sides of rectifiers using silicon rectifying elements. Their use on units using selenium elements is recommended in areas where lightning strikes are frequent. The arrestors on the output should have a firing voltage greater than the rectifier output voltages. With regard to the decision of selenium versus silicon stacks, while some old installations used copper oxide rectifying elements, modern units use either silicon or selenium rectifying elements. In general, silicon units are used for larger units where their higher efficiency is more important than their lower reliability. Ordinary selenium stacks deteriorate with time. This aging can be reduced by variations in plate composition, and non-aging stacks are available. Aging rates are determined by operating temperatures that are a function of current flow. The selection of a unit using selenium rectifying elements which has a somewhat greater capacity than required will increase stack life. The efficiency of selenium rectifying elements is a function of operating voltage versus rated voltage as shown in Figure 11. Silicon diodes are mounted in metal cases which are mounted on either aluminum or copper plates to dissipate the heat generated during operation. Silicon diodes do not age as do selenium stacks, and as shown in Figure 12, are more efficient than selenium elements, particularly at high voltage ratings. Silicon rectifying elements are more subject to complete failure from voltage surges, which would only cause increased aging of selenium stacks. Surge protection should always be used on both the AC input and DC output of rectifiers using silicon diode rectifying elements. Other features are available and should be selected as appropriate. In remote off-base areas, small arms proof enclosures may be required based upon local experience. Specifying clear anodized aluminum enclosure top coated with one clear coat of polyurethane will reduce maintenance painting. The AC current requirement for a rectifier can be determined based upon rectifier output and efficiency by the following formula. Figure 11 is the efficiency versus voltage for selenium stacks. Figure 12 provides the efficiency versus voltage for silicon stacks. Although any electrically conductive material can serve as an anode in an impressed current system, anode materials that have a low rate of deterioration when passing current to the environment are mechanically durable. These anode materials are available in a form and size suitable for application in impressed current cathodic protection systems at a low cost. While abandoned in-place steel, such as pipelines and rails, can and are used as anodes, they are consumed at a rate of about 20 pounds per ampere year. The most commonly used purchased materials for impressed current anodes are graphite, high silicon cast iron, high silicon chromium bearing cast iron, aluminum, platinized titanium, platinized tantalum, platinized niobium, and silverized lead. Newly developed anode materials such as oxide-coated ceramics show considerably promise and should be evaluated based upon experience in similar applications, particularly if the more commonly used anode materials have proven unsatisfactory in a specific application. Graphite anodes are the most commonly used material for impressed current anodes in underground applications. They are made by fusing coke or carbon at high temperatures and are sealed with moisture penetration by being impregnated with a synthetic resin, wax, or linseed oil to reduce porosity and increase oxidation resistance. An insulated copper cable is attached to the anode internally for electrical connection to the rectifier. The connection must be well sealed to prevent moisture penetration into the connection and must be strong to withstand handling. The most important single improvement in high silicon cast iron and graphite anodes is placing the lead wire connection in the center of the anode instead of the end. This eliminates end effect, which ends of the anode are consumed 1.5 times faster than the center. Although more expensive, the anode life is nearly doubled. Tubular anodes will be 95% consumed, whereas end-connected anodes will be only 50% consumed before the anode to lead wire connection is lost. This also allows for a more effective seal of the lead wire connection. Nearly all anode sizes are available in tubular form where the lead wire connection is located in the center. Typical anodes, connections, and seals are shown in figures 13 and 14. The following are typical specifications for commercially available graphite anodes. The composition and physical properties and mechanical requirements are as shown. Graphite anodes are commercially available in 2 sizes as indicated here. The weights given are for the graphite only and do not include the weight of the lead wire or connection. Figure 13 indicates the anode to cable connection for a graphite anode. Figure 14 indicates a center-connected graphite anode. All products from the operation or deterioration of graphite anodes are gases. In freshwater or non-saline soil, the principal gases produced are carbon dioxide and oxygen. In saline soils or in seawater, chlorine is also produced and is the major gas produced in seawater applications. The gases generated, if allowed to collect around the anode, can displace moisture around the anode, which results in a local increase in soil resistivity and an increase in circuit resistance. Graphite anodes must be installed and operated properly in order to ensure optimum performance in life. The current densities in the following table should not be exceeded in order to obtain the optimum anode life. This table indicates the recommended maximum current density for graphite anodes in seawater, freshwater, and soil. Since the potential difference between steel and graphite is approximately 1 volt, with the graphite being the cathode, this potential difference must be overcome before protective current will begin to flow in the impressed current cathodic protection system circuit. This 1 volt must be added to the other voltage and IR voltage drop requirements during the selection of proper power supply driving voltage. Assuming uniform consumption, the rate of deterioration of graphite anodes in soil and fresh water at current densities not exceeding the values in the table above will be approximately 2.5 pounds per ampere year. The deterioration rate for graphite anodes in seawater ranges from 1.6 pounds per ampere year at current densities shown below 1 ampere per square foot to 2.5 pounds per ampere year at current densities of 3.75 amperes per square foot. The deterioration of any point on a graphite anode is proportional to the current density at that point. If the resistivity of the environment at any one point is lower than the resistivity at other points, the current density and attendant deterioration will be higher there. This can result in uneven consumption and premature failure of graphite anodes, particularly if the low resistivity area is near the top of the anode. In this case, necking of the anode at the top occurs and the connection to the lower portion of the anode is severed. The use of backfill of uniform resistivity is used when graphite anodes are used in soil in order to prevent anode deterioration. Cast iron containing 14 to 15% silicon and 3/4 to 1% other alloying elements such as manganese and carbon form a protective film of silicon dioxide when current is passed from their surface into the environment. This film is stable in many environments with the exception of chloride-rich environments. The formation of this film reduces the deterioration rate of this alloy from approximately 20 pounds per ampere year, as for ordinary steel, to 1 pound per ampere year. Due to the lack of resistance of this alloy to deterioration in environments containing chloride, a chromium-bearing alloy of similar silicon and other alloy content has been developed. The chromium-bearing alloy is now almost exclusively used. High silicon chromium-bearing cast iron anodes are widely used for impressed current anodes. Being a metal, it has much greater mechanical strength than non-metals such as graphite magnetite. However, due to its low elongation under load, it is brittle and should be protected from both mechanical and thermal shock. The nominal composition of high silicon chromium-bearing cast iron is as follows according to ASTM specification A518. And the elements and their percentages are as indicated on this table, and the physical properties are as shown. High silicon chromium-bearing cast iron anodes are available in a wide variety of standard sizes and shapes as shown in tables 8 and 9. Special configurations can be produced at extra cost and are usually practical when standard anodes have been shown to be unsatisfactory for a particular application and where a large number of special configuration anodes are required. Typical anode configurations are shown in figures 15 through 19. The cable to anode connection is, as in the case of all impressed current anodes, critical. Three common methods of achieving the cable to anode connection and seal are shown in figures 20, 21, and 22. The use of the center-connected tubular anode, as shown in figure 23, is preferable as necking of the anode at the connection point is avoided and life of the anode is extended 90%. 50% anode material expended before failure versus 95% anode material expended before failure for center-connected anodes. Cast iron anodes of this alloy are consumed at a rate of 1 pound per ampere year when used at a current not exceeding their nominal discharge rates. The potential difference between steel and cast iron can be neglected in the selection of impressed current rectifiers. High silicon chromium bearing cast iron anodes will operate without backfill in most applications, but backfill will reduce the anode to electrolyte resistance and extend the life of the anodes. Because metal-to-metal contact is made between the anode and the round particle calcined petroleum coke breeze, the outside of the coke breeze becomes the anode. Also, the lower output voltage required will save power and reduce the initial cost of the rectifier unit. Because of these reasons, petroleum coke backfill is recommended where it can be feasibly installed. Aluminum anodes are sometimes used for the protection of the interior of water storage tanks. They are consumed at a fairly high rate of approximately 9 pounds per ampere year in most applications. The main advantages of using aluminum anodes in the protection of water storage tanks is their low cost, lightweight, and lack of water contamination from the products of deterioration of the anodes. They are commonly used when seasonal icing of the tank would damage the anodes. The aluminum anodes are sized to last 1 year and are replaced each spring. High silicon chromium bearing cast iron and graphite anodes are more commonly used in water tanks and when installed on a floating raft can be made resistant to icing conditions. Pure platinum wire is sometimes used for impressed current cathodic protection anodes where space is limited. Platinum is essentially immune to deterioration in most applications. In seawater, its consumption rate at current densities as high as 500 amperes per square foot is 0.00001 pounds per ampere year. Due to the high cost of platinum, this material is more commonly used as a thin coating on other metals. Platinum can be bonded or deposited on other materials for use as an impressed current cathodic protection anode. The substrate materials, namely titanium, tantalum, and niobium, have the special characteristic of being covered with a naturally formed stable oxide film which prevents current flow from their surfaces, even when exposed to high anodic potentials. All of the current flows from the platinum-coated portion of the anode surface. These platinized anodes, although high in initial unit cost, can be used at very high current densities and have had wide application to service in tanks and other liquid handling systems as well as in seawater. Their use in soils has been limited occasionally to deep well applications. Table 8 provides descriptive characteristics of standard high silicon chromium bearing cast iron anodes. Table 8 is continued here. And Table 9 provides characteristics of special high silicon chromium bearing cast iron anodes. Figure 15 indicates a duct anode. Figure 16 is a detail of a button anode. Figure 17 is a detail of a bridge deck anode type 1. Figure 18 is a detail of a bridge deck anode type 2. Figure 19 is a detail of a tubular anode. Figure 20 is an anode to cable connection with an epoxy seal. Figure 21 is an anode to cable connection with a Teflon seal. Figure 22 is a center-connected high silicon chromium-bearing cast iron anode. The types of platinized anodes are available in a wide variety of sizes and shapes. The sizes of standard platinized titanium anodes are shown in this table. A typical anode configuration is shown in Figure 23. Figure 23 indicates a typical platinized anode. Platinized anodes can be operated at very high current densities. 100 amperes per square foot is typical. The primary limitation of platinized anodes is that the oxide film on the substrate can break down if excessive anode to electrolyte voltages are encountered. The practical limit for platinized titanium is 12 volts. Platinized niobium can be used at potentials as high as 100 volts. Since these anodes are small in size, their resistance to electrolyte is high, and therefore higher voltages are required to obtain high current. Lead alloyed with silver, antimony, or tin have been used as anodes for impressed current cathodic protection systems in seawater. The chief advantage of lead anodes is their low cost. The consumption rate for silverized lead is 2 to 3 pounds per ampere year initially, but drops off to approximately 0.2 pounds per ampere year after 2 years. The current density from silverized lead anodes is typically 10 amperes per square foot. Alloyed lead anodes have been unreliable in many specific applications, either because they failed to passivate and their consumption rate remained in the 2 to 3 pounds per ampere year range, and they were completely consumed, or they became so highly passivated that the anode to electrolyte resistance increased substantially. In addition to the source of power for cathodic protection and the anodes used, cathodic protection systems contain other important components. The entire system must be reliable in order to provide effective protection. The connecting cables used between the various components of cathodic protection systems are vital to the proper performance of the system. Any break in the primary circuit will result in failure of the system and will require repair to restore the flow of protective current. Breaks in the auxiliary connections, such as those used to test the system, will also result in difficulties in proper adjustment and inspection of the system. Proper selection of cable size, type of insulation, and routing is necessary for proper and reliable system operation. Only insulated copper cables should be used in any cathodic protection installation. High connection resistances and difficulty in making welded connections associated with the use of aluminum wires precludes their use in cathodic protection installations. Factors to be considered in connecting cables: they should be selected based upon consideration of the following: the current carrying capacity, the voltage attenuation, the IR drop, current times resistance, the mechanical strength, the economics, first cost versus power cost, dielectric strength of insulation, durability regarding abrasion and cut resistance of the insulation, and standard wire sizes, weights, and breaking strengths are given in Table 10. Table 10 provides standard wire characteristics. The connections between the cathodic protection power source and the anodes are usually submerged or buried at least over part of their length. These cables are extremely susceptible to failure as they are operated at highly positive potentials. Any contact between the metallic conductors and the environment will result in rapid deterioration of the conductor and loss of continuity of the protective circuit. Anode lead wires should never be used to suspend, carry, or install the anode except in water storage tanks. High molecular weight polyethylene insulation has proven to give satisfactory service for the installation of this critical connection in most shallow buried applications. Where exposure to chlorine is encountered, such as in seawater or in deep anode applications, chlorine-resistant insulation such as fluorinated ethylene propylene, tetrafluoroethylene, and polyvinylidene fluoride are used either singly or in combinations with thicknesses of up to 0.15 inches. These materials are also used over a primary insulation of extruded polyalkene 0.3 inches thick, or are covered with a jacket of high molecular weight polyethylene for mechanical protection. A highly successful insulation for such highly critical applications has been a system consisting of 0.065 inch thick high molecular weight polyethylene outer jacket for abrasion resistance combined with a 0.04 inch thick ethylene monochlorotrifluoroethylene copolymer. For less critical applications such as the negative lead to the rectifier, test wires and above ground wiring, thermoplastic insulation type TW, synthetic rubber RHW-USE, or polyethylene may be used. Because of similarities in required characteristics of the various connecting cables in many impressed current cathodic protection systems, general specifications for cable sizes and types for many cathodic protection system requirements have been established and are given in the next table. Test wires. These wires carry only very small currents, and as they are themselves cathodically protected, insulation requirements are not critical. Solid copper wires, number 12 gauge AWG with type TW-RHW-USE or polyethylene insulation should be used for this application unless otherwise indicated by experience. As to bond wires, these wires carry more current than test wires. Number 4 AWG 7-strand copper cable with type TW-RHW-USE or polyethylene insulation is recommended for all bonds unless a larger wire size is required for current carrying capacity. With regard to the power supply to structure cables, the power supply is HMWPE insulated 7-strand cable, usually in the size range of number 2 or number 4 AWG. The actual wire size should be determined by economic analysis, but wire no smaller than number 4 AWG should be used because of mechanical strength required. For the power supply to anode cable, the insulation in these cables is critical. HMWPE insulation 0.110 inches thick as a minimum is required on these cables. The anode connection wire is usually number 8 AWG with HMWPE insulation. The wire used to interconnect the anodes and to connect the anode bed with the power supply is commonly in the range of number 2 AWG or larger. The actual wire size should be selected based upon the economic analysis, but should not be smaller than number 4 AWG because of strength requirements. The size of the connection between the structure, anode bed, and power supply in impressed current cathodic protection systems should be selected to minimize overall cost. This can be determined by calculating the annual fixed cost of the selected wire and comparing it with the cost of power losses for the system. When the annual fixed cost and the cost associated with power losses are equal, their sum is minimum and the most economical selection of wire size is confirmed. If the power losses exceed the annual costs, a larger wire size is indicated. If the annual fixed costs exceed the power loss, then a selection of a smaller wire size would be appropriate. The formula for determining power loss costs is as indicated on this slide. Wire splices and connections are a source of undesirable circuit resistance and are a weak point in the reliability of the system, since they often fail due to corrosion or mechanical damage. The number of connections should be kept to an absolute minimum, and the type of connection used should have a low resistance, high reliability, and good resistance to corrosion. Both mechanical connections and thermal weld connections are used in the installation of cathodic protection systems. Mechanical connections are less expensive than thermal weld connections, but often have higher resistance and are more susceptible to corrosion and mechanical damage. All connections must be carefully insulated, particularly in the anode to power supply portion of the circuit, where any loss of insulation integrity will result in rapid system failure. All connections in the power source to anode bed portion of the circuit and all cable-to-cable connections should be insulated by encapsulation in epoxy using commercially available kits made expressly for this purpose. The cable-to-structure connection is less critical, and either epoxy encapsulation or insulation with hot coal tar enamel followed by wrapping with pipeline felt may be used on this connection. The following connections are required for impressed current systems. Connection between power source and structure. Connection between anode beds and power source, the anode head cable. Connection between anode header cable and each anode. Connection between cable and anode, usually factory made, and necessary bond and test wires. The need for additional connections and splices should be carefully evaluated. The location of all necessary splices and connections should be specifically shown on the design drawings. The need for additional splices and connections should be determined by the designer of the system and not left to the discretion of the installer. Table 11 indicates the M factors for determining economic wire size, the cost of losses in 100 feet of copper cable at 1 cent per kilowatt. There are 6 basic types of test stations used in impressed current cathodic protection systems. The potential test station, the soil contact test station, the line drop IR drop voltage test station, the insulating joint test station, the casing insulation test station, and the bond test station. The wiring for each of these test stations is shown in figures 24 through 29. Test wires should be solid copper, number 10 AWG, either TW or RHW USC insulated. If future bonding across flanges or between structures may be required, 7-strand copper cables, number 4 AWG or larger if required, should be connected to the structures and brought into a test station for future use. Test stations may either be located flush with the surface of pavement or soil as shown in figure 24, or in an above-grade test station as shown in figure 27. Manufactured specifically for this purpose, flush-mounted test stations are preferred in paved areas or other areas where damage by vehicles, etc. is anticipated. Above-grade test stations are preferable in unpaved areas. In addition to test stations, balancing resistors are sometimes required when multiple anode beds are used with a single rectifier. These resistors should be installed in an above-grade terminal box as shown in figure 30. The location and wiring of all test stations should be included in the system design. All test wires should be color-coded and marked with non-corroding metal or plastic identification tags indicating what they are connected to. Bonds between sections of the protected structure or between the protected structure and a foreign structure should use 7-strand copper cable, number 4 AWG or larger insulated cable. All resistive bonds should be brought into a test station for adjustment. Direct bonds may also be brought into test stations if future adjustments or connections may be required. All bond to structure connections should be made using thermoweld connections insulated by epoxy encapsulation. Standard details for bonding are shown in figures 31 through 38. Insulating joints between sections of a structure are often installed in order to break electrically the structure into sections that can be protected by independent cathodic protection systems, or to separate sections that require cathodic protection from those that do not. These joints can either be directly buried or be located in valve pits or be located above grade. If they are directly buried, they should be furnished with a test station as shown in figures 39 through 42. Figure 24 indicates a flush-mounted potential test station. Figure 25 indicates a soil contact test station. Figure 26 indicates a voltage IR drop test station. Figure 27 indicates an insulating flange test station, 6 wires. Figure 28 indicates wiring for casing isolation test station. Figure 29 indicates a bond test station. Figure 30 indicates an anode balancing resistors station. Figure 31 indicates the method of bonding of a dresser style coupling. Figure 32 indicates bonding methods for cast iron bell and spigot pipes. Figure 33 indicates isolating a protected line from an unprotected line. Figure 34 indicates a method of electrical bonding. Figure 35 indicates a thermosetting resin pipe connection. Figure 36 indicates a clamp type bonding joint. Figure 37 indicates an underground splice. Figure 38 indicates a welded type bonding joint for a slip-on pipe installed above ground. Figure 39 indicates a test box for an insulating fitting. Figure 40 indicates a steel insulating joint detail for flanged pipe installed below grade. Figure 41 indicates a steel insulating joint detail for above ground flanged pipe. Figure 42 indicates insulating joint details for screwed pipe connections. And that brings us to the conclusion of this brief discussion of impressed current cathodic protection systems. I hope this was about what you were looking for, and that this gives you some new and useful information that you will be able to use moving forward to address cathodic protection and impressed current cathodic protection issues as they come across your desk in the future. Again, thank you very much for letting me chat with you, and have a nice rest of the day.